Good afternoon to everybody who decided to participate in Sano seminar on this Monday. And this is a continuation of overview of research of PhD students at different research team of Sano. And today, as a speaker, we host Sabina Kamińska. She's working on his PhD in the framework of health informatics team. We have with us also leader of this team, Przemysław Korzeniowski. Przemku, well, maybe it will be the best if you could introduce Sabina and her research.
Okay, great. Thank you, Marian. Yes, so Sabina is a biomedical student. She started with us in 2022. So her project is about deep learning, in particular reinforcement learning for training surgical robots, basically. So you may wonder why this idea, why such projects appear at Sano. So this is dates back to a couple of years ago when, as you may know, my background is in virtual reality surgical simulators for surgical training. And I was contacted by a few well-established research groups in surgical robotics from Europe, among others, the University of Verona, Altai Robotics Lab, Karlsruhe Technical University in Germany, as well as Hamlin, the Imperial College London. And they contacted me because they find my simulators really attractive, like piece of software for them to train, to use them as virtual environments for efficiently training surgical robots to perform like a basic surgical tasks. And when I was in the early days of sort of discussing me potentially joining Sano, that was one of the topics. Actually, it was one of the main motivations for me joining Sano to basically to do such projects, but on our own. So I had the simulators well developed, some even commercialized. And Sano could offer sort of AI expertise, so we could combine it together. So hence like the story behind this project. And as you may know, I'm sure Sabina will tell you more. Surgical robotics is currently booming. Like patents for the Da Vinci surgical systems are slowly expiring. Intuitive Surgical, company behind Da Vinci robot, which is most common robot. I think there's more than a couple thousand now deployed worldwide. They had 6,500 patents for the robots. So these patents are slowly expiring. Da Vinci was released more than 20 years ago. Currently, there is version 5 of the system, Mark 5. And there is more and more competition from all over the world, from the States, from Japan, of course, from China, even from India. So the companies who are developing surgical robots. Also, it's worth noting that in Poland, especially in Poland, we'll have like a huge problem with surgeons in a couple of years. Average age of a surgeon is 59.5, last time I checked. Young clinicians, they don't want to train to become a surgeon because of various reasons. Don't want to get into details. So surgical robotics may offer like capacity at least to decrease the cognitive load of a surgeon, of surgeons, decrease the number of complications, decrease the surgical time, hence improve the surgical healthcare in general. So I think I said enough. Thank you very much, and Sabina, the screen is yours. Thank you.
Thank you so much for a nice introduction. So good afternoon, everyone. I would like to present the topic of my research is deep learning based surgical robots. I am from health informatics team, conducted by Przemysław Korzenowski. So I want to highlight the process in robotics achieved through simulation, synthetics data generation, and interaction-based learning. Simulation is a powerful tool that creates digital clones on the real world, generating large-scale data set to train and test autonomous system on a large scale. So simulations have been used for decades to test and optimize safety critical design and algorithms in various industries. In robotic research, simulations are used to develop planning and control strategies through reinforcement learning. However, simulations have not significantly impacted robotic assembly yet. Most previous efforts to solve assembly tasks have focused solely on real-world development. This approach is very effective, but typically require substantial human effort for mechanical design, trajectory planning, demonstration, correction, or resets. Moreover, they can be difficult to scale to a broader range of assembly problems. We take a simulation-first approach because of its long-term potential to leverage large-scale computing with reduced need for human input. Minimally invasive surgeries have advanced from using handheld tools to employing the intuitive Da Vinci surgical system, which offers master-slave teleoperation control and wide range of robotic arm movements. Enhanced dexterity in surgeries has the potential to lower surgeon cognitive load and shorten the learning curve. So research in the field of augmented surgical dexterity covers tasks such as pattern cutting, suturing, and needle tracking. However, these efforts often depend on access to expensive surgical robotics hardware, and developing robust models typically require collecting large and costly data sets to generalize to new environments. This creates a significant barrier for researchers to make progress in these fields. The aim of this work is to enable scale learning for surgical autonomy. Simulating surgical environments is challenging due to the complex interaction between rigid and deformable components and the limited range of arm motion. Our efforts are focused on developing a surgical robotic simulator that imitates reality much faster than real time, supports rich physical interaction, and provides high fidelity rendering to bridge the visual simulation to reality gap. The simulator will have access to robot learning frameworks, be capable of recording human experts data for policy learning, and run successfully on physical platforms. Learning at scale has been difficult by absence of easy-to-use, high-quality simulation framework for surgical robotics. Previous state-of-the-art simulator in this field have faced challenges such as limited rendering capabilities, a small number of available surgical environments, and a lack of native support for deformable objects. Moreover, the absence of GPU-accelerated physics has been a major obstacle for learning. Consequently, creating a surgical robotic framework that integrates accurate physics, provides high-speed realistic rendering, and supports various robot learning tools remaining an ongoing challenge. Table 1 offers a comparative overview of open simulation framework for surgical robotics. Additionally, we compare the performance of different simulator in environments of similar complexity, specifically in tasks involving robot reach, rigid object manipulation, and soft object manipulation. Here we are present the open source frameworks that are the most interesting and that we have researched. Is the Sano from 2021, LabGym from 2023, and new one, Orbit Surgical. So in my work, I use PPO and as a most popular deep reinforcement learning algorithm. It runs reasonable fast by leveraging vector environments and naturally works well with different action space. It was like taking smaller policy updates to improve the training stability. So in this case, we see PPO training similar to LabGym, but based on real RL games. I trained it using PPO. In the video attached, we see tissue with a grasper. The lesion concerns tissue retraction. The system of tissue retraction relies on reward and penalties. The penalty decrease as the distance of designed point decreases. Controversy rewards are given when the tip of the laparoscope reach the designed target. Like in these cases, there's two targets on the tissue for grasping, and the final one to reach the retraction point. Additionally, the system is penalized if the tip of the laparoscope goes outside. It's called like a safe area. The training will be completed when a sufficient number of points determined based on try and errors have been accumulated. Here we see the first result of tissue retraction. The task is to reach the laparoscope to the place of grip on the tissue, and drag is to given point in the order to reveal the purple dot. So we have two action: approach, grasp, and retract. So something about the Riemann motion policy we are using on our X-arm arm 7 in simulation. Broadly defined, a motion policy is a mathematical function that takes the current state of a robot, position and velocity in generalized coordinates, and returns a quantity representing a desired change in that state. So such a policy may depend implicitly on variables representing one or more objectives or constraints. The state of the environment, an acceleration policy in a motion policy where the output is desired acceleration resulting in a second order different equation. A Riemann motion policy called RMP is an acceleration policy accompanied by a matrix that is sometimes called an interior matrix, borrowing terminology from the classical mechanics, but also closely related to the concept of Riemannian matrix. So in this video, we see to task, pick, and place motion policy, as I mentioned before on our X-arm robot, and articulation motion policy. We developed a surgically focused simulator. We can observe how FSRL obtains a higher FPS throughput than LabGym, guaranteeing significant performance and increases. If we consider a single environment, FSRL guarantees a performance increase over of over 6 times with respect to the lab gene. Lab gene is the previous one, previous open source framework. If we consider 4 environments, we have an increase of more than 8.5 times, with becomes over 30 with 8 environments. The maximum number of environments supported by a lab gene on the hardware configuration considered. However, FFSRL can also run on 16 and 32 environment, as we see on this image. In parallel, guaranteeing a further increase in performance compared to the configuration of the 8 lab gene environments of 20 and 26 times respectively. We should know that we were not able to run more than 32 environments during reinforcement learning training on the considered system. This reduction compared to the simulation alone capable of reaching 18 environments is linked to the limits of the graphics memory. The limit of the 80 simulation environments in parallel is rather concerned with the available system memory. So our next topic is stable diffusion. Is very side in that it can be used in a number of different ways. The word diffusion describes what happens in this component. It is the step-by-step processing of information that leads to a high-quality image being generated in the end by the next component, the image decoder. Diffusion happens in multiple steps. Each step operates on an input latence array and produce another latence array that's been resembles the input text and all the visual information. The model picked up from all images that the model was training on. Due to the fact that Joanna Caleta from Sano worked on stable diffusion and was awarded in the International Journal of Computer-Assisted Surgery and Radiology on workshop on diffusion models, and she won Best Student Paper Award sponsored by NVIDIA. We decided to continue working on this topic. On this slide, we see image from a simulator and her corresponding result after applying stable diffusion. We see image with high fidelity. So on this slide, we see the cholecystectomy procedure. As we see that the red one place is liver, gallbladder, pink one, and tissue with the abdominal wall. In her work, it was used a combination of different styles. She calculated mean intersection over union, average interception distance, and the kernel interception distance. And as we can see, she obtained a good result in these cases. So in my approach, we utilize our simulator with realistic texture and lightening in contrast to the previous approach. Additionally, we will add a realistic DaVinci device that's being implemented into the simulator as shown in the attached image. So like the grasper, scissors, and more advanced instruments. In the future work, I will also add more complex instruments. So in attached screenshot, we see my initial results, achieving good results with the real textures is more challenging. So we can wondering why I start working on the on stable diffusion. That's why I would like to enhance deep reinforcement learning with general high realistic image. This image can aid in visualization and preliminary training of deep reinforcement models, improving pattern and object recognition. Furthermore, generating various scenes and situations increase data diversity. The generated images can present different types of tissue, lightening condition, viewing angles, and which help in generating verify model capable of generation. So we have the first metrics. The mean intersection over union value of instrument is lower, is due to instrument problem because we are working on not Da Vinci tools. And changing instrument, we think that helps receiving good results. Okay, so we on this slide we see heat maps. We see the problem with the instruments on the prediction to real image, and also we are trying to figure out what's happened with the abdominal work. So the results so far, I developed simulated surgical environments. We are develop simulated surgical environments which are not only realistic but also computationally efficient and scalable to tackle this issue. The first reached to point and direct traction on simple tasks. We are develop also RPM trajectory on X-arm 7. And the first realistic development, the first realistic tissue result of cholecystectomy surgery based on realistic simulator. Future work, we would like to compare training to orbit surgical platform and work on it, and apply full task with visual observation that add more complex tasks, and finally transfer sim to real. So our publication, we have accepted paper on the Hamlin Symposium. It will be held on in June this year. There is the GPU-based simulation for surgical robot learning. Also, we have in process on ICRA the same paper with high performance GPU. What we have planned, we would like to apply with the stable diffusion, the paper realistic endoscopic synthetic data generation via surgical simulation and diffusion models on deep generative models workshop on medical image computing and computer assisted intervention this year. Collaboration, we are working with Paul Maria Shaker, who is the author of open source framework LabGym. Also, we are working with Diego Dal Alba from University Verona, and also I'm working with my team leader, Dr. Przemysław Korzeniowski and Michał Naskręt. So thanks for attention.
Thank you very much for this short and quick overview of your research. Well, now we have time for a discussion, for questions, and let's say which will be a kind of opportunity to get more information about your research. Well, before some questions will appear from participants, and on one of your, well, I think that it was one of the latest slide on the list of your achievements. You mentioned that you have elaborated something which is scalable. So if you could give more detailed information about the scalability of your system.
So the scalability of our system can help the surgeon. We are focusing now on the tissue retraction that's held the 80% time surgeon in their work. So it's help him. It's help to reducing time and focus on critical aspect on the surgery. So like that's why it's scalable. Maybe Przemek can also add if he wants.
Well, but it means that it is scalability of a time for finding a solution against what? So this is what I do not understand, because usually scalability means that if you have something 2 times more, you need, for example, 2 times more time to solve the problem. And what is scalability in this case? So this is what.
Thank you, Marian. Yes, scalability in this context means that when we develop the FSRL, it's both simulation and training runs on the same GPU. So it's very fast to train, and we can scale it quite nicely in sense that we can run massively parallel simulations. So we can have like even hundreds, if not thousands, of parallel simulation environments running just on a single like NVIDIA 800 with 80 gigabytes of the memory. I think as far as I remember, Michał ran tests and he managed to run more than 1,000 environments, but without learning. So the main memory cost is when we are using visual observation, which means that the training is based on what the virtual endoscopic camera sees, and then the convolutional neural networks, they use quite a lot of memory in this sense. But yes, so just adding another GPU to the training or having GPU with more memory, we can linearly scale and scale the number of environments and decrease the training time.
And about these environments, they are somehow how they are selected, how they are chosen. They are standard situations, or is
yes, so,
to which extent is your choice, or to which extent it is somehow common in this type of research?
Yes, so in recent, really like 2 years, there were some projects like LabGym when they had like a couple of environments and couple of basic surgical tasks. So for example, like revealing this retraction when we have just, it's not non-anatomical case, which means we have just a block, like a cube of deformable body, and we need to lift it to expose what is underneath. So there's I believe there's something around 10 different environments like this, something you need to pass from one instrument to another. Like they're pretty basic, but our ambition is to have anatomical cases, so something that looks like a surgery. Right now, I guess Sabina showed this is so this liver and instrument, this we can consider this like a single environment, and we want to have this fully anatomical, which means this resembles like a real surgical procedure. So our aim is to drastically improve both the simulation the quality of the simulation, the realism of the simulation, as well as performance of the simulation, hence to using GPUs very, very efficiently. And the next stage, like what Sabina told in the second stage of the part of her presentation, we also want to drastically improve the visualization, because we don't only want to train things virtually, but in the end, we would like to move it to the real world. We would like to move the policies trained in a virtual environment, be transferred, so this is called sim to real, simulation to reality, into the real world.
I understand. Thank you very much for this explanation. Well, and I have also a question about, because I know that Szymon Płotka, who is one of the co-author of your paper, is, in my opinion, far away from surgery. But what was his? Do you have used something he has discovered elaborated in his research on weight estimation, or?
No, so Szymon helped with his expertise in writing and drafting papers.
Oh.
And he also helped me with the validation studies of Spina Bifida simulator, which is one of the cases we would like to simulate. So when we were running this in Bielański Hospital, I believe.
I understand. Yes, and we have Wiesław now with us. Wiesław, yes, go on, please.
Yeah, thank you, Marian. It's a nice work. Yeah, surgical simulation is always an exciting topic. My question is first about positioning of this work, because it was mentioned that some companies like Intuitive, they have thousands of patents in this field. So how are you sure that what you are doing is completely novel and you are not reinventing the wheel?
The new one, because we are working directly only on GPU. The least one, as I see on the table one, is the new one, newer frameworks. We are not checked it yet, but we will. We are comparing to LabGym, and they only work on the CPU, not on the GPU. Working on GPU is makes faster, as Przemek mentioned before. And we also, in this case, we can work on the object where supported dynamic. So that's why it's the state of the art. And we, in this case, we see only the simply frameworks. That's only for training. They are not used the complex tissue like you are see on our approach, like the liver. There's only, like I showed before, I show there is only a tissue, because in these cases I was trying to compare only on GPU the PPO training. So
thank you, Sabina. I guess Wiesław was asking on the higher level and not in the details. So indeed, Intuitive Surgical, who was the pioneer of surgical robotics and is most established company by huge margin still at the moment. So the patents are from, I guess, wide variety, including hardware to large extent. So I'm not aware, to be honest, whether they have patents, and for sure they are interested in autonomy, because I've been following the workshops that are sponsoring, and the challenges, for example, that we are often, our team is taking part. For example, the end of these challenges from Mikai, they're quite often sponsored by them. So last seminar at Hamlin, where we were participating, they were. I don't think they are still like going all into autonomy. They are looking at different things of especially understanding the scene at the moment. So I don't think what I'm trying to say that we are not competing with them in any way, especially on patents in terms of surgical simulation or autonomy. I guess what is interesting here that we can improve both simulation and visualization, not only by using like a better simulation in terms of numerical methods or more efficient, but we can combine it these days with also with artificial intelligence. So data-driven methods of approximating real world. So just to give an example, because that may explain it better. So for example, we can have low resolution fast simulation running on the GPU. And then on top of this simulation, we can do predictions with artificial intelligence to further improve the realism of the simulation. So a short example from NVIDIA. So they were using this approach. They managed to decrease like a weather prediction, global weather prediction from weeks into hours, for example. We can use, of course, real data, or we can from real world, which is in surgery difficult, maybe not difficult to acquire, but difficult to label, especially by hand by surgeons. No one wants to do it really, or it's very expensive. Or we can use high quality offline simulation data, for example, to improve the simulation. And the same goes with visualization. So we can go using traditional 3D graphics like ray tracing, trying to make it look better, just add another like few hundred millions of triangles. But I guess that's or we can use basically this prediction, the stable diffusion that Sabina was talking about. So the research is really on the state of the art. The stable diffusion work was awarded, like Sabina mentioned, like a best student paper award on the workshops on diffusion models. But that was at NeurIPS. So NeurIPS is currently like a top ranked conference on artificial intelligence.
Mm-hmm.
So I guess there's still place to make an impact. And because it's more like a software, I mean, we were less worried about the patents. I hope I managed to answer.
Thank you, Przemek. Yes, in fact, my question was more general in the sense that, maybe some topics you have been working on are so novel that the basically researchers might be not aware because they don't do any patent searching, and they would say, oh, no one has been combining robotics with graphics, with artificial intelligence. And at the end of the day, it might be a huge market niche, and Sano might be sitting on the golden mine without knowing that. So therefore, my suggestion would be maybe from time to time it's good to do some patent searching and see that what you have been doing, it's really so exciting and novel, and has a great potential in the future to protect some market niche.
Yes,
Just
thank you.
as thought.
So for sure, we are still like building this critical mass, but we will definitely, when we generate more results, look into patenting. So actually, I guess our main competitor now is in fact not Intuitive Surgical, but NVIDIA released like literally a few weeks ago. It was published at ICRA, so top robotics conference. Or it's called Orbit Surgical. So it's very similar in spirit. It's also using GPU for both simulation and training. Yeah, so the bottom right of the training. Yeah, so actually you can see like they have like 14 different environments. But I discussed with the last author of the paper and the whole framework, Animesh Garg, who is one of the leading, most well-known person in I would say even like autonomous robots. So he's both in Toronto University, but he's also a senior researcher at NVIDIA. And he told us that he sees a lot of point in what we are doing, that we are creating like a custom physics engine, basically, particularly for surgical simulation. They are using something that was developed for rigid bodies, and even like for games where we have like large static worlds and some moving objects. Then they adapted it for sort of industrial robots. So he said that, okay, we got this orbit surgical, but for example, we're not able to do it like any tissue cutting or coagulation or even suturing, which is omnipresent in surgery. Right, and they also what they are using their physics engine, physics from NVIDIA. Their GPU version is closed source.
Yes, I think it's another evidence showing that what we are doing is novel, that we are pioneering some work. And of course, after having more results, after publishing more results, we are closing the way of patenting it, because whatever is patented, whatever is disclosed cannot be patented. Yeah. Another question is, yeah, deformations are beautiful, but these are only geometric or physical deformation. Do you really calculate physics behind? And if yes, what is the source of getting parameters, or this is pure geometric deformation?
Yes, so this is something that we that I mentioned about this data-driven approach. So I discussed this with one of the Ferdinando Baena from Hamlin, like a director of Hamlin, so Institute for Surgical Technology in London at Imperial, and they are, I don't want to say like losing faith, but they are like skeptical whether they can get the realism needed of such viscoelastic behavior of human tissues using numerical methods. So they are leaning towards data-driven approach, especially the one I mentioned, that you have more or less the simulation, coarse simulation, quick one, and then the missing detail about the elasticity, the plasticity of the tissues is filled in by real data or high quality simulation data. So the method we are using under the hood, it's so-called physically based simulation. It's using position-based dynamics and neo-Hookean model. So it's implementing current state of the art. But I guess the deformation itself is not important as what we want to achieve in the next stages. So things like cutting, coagulation, and suturing. These are like real, I would say, real challenges, topological modifications and suturing.
What do you think? What will be the future outcome? You plan to start a startup? Or are there any companies in Poland who might be interested to develop a product?
So we would more considering us like providing our trained models, for example, to third parties. So NVIDIA, for example, they have their let's call it supercomputer for an operating room. It's called NVIDIA Clara. In fact, they sent two devices to us like more than a year ago. So this is basically like a powerful GPU RTX 6000 with this NVIDIA Jetson system on a chip, and but it's medically certified. So we can put it in the operating room and meets all the standards of electricity and I do not know exactly the details what are the standards, but it's certified that it can be plugged in basically in the operating room. But what's more interesting, so they are working already with Karl Storz, who is main provider of laparoscopic stacks. So visualization of the abdomen, not only abdomen, but basically laparoscopes and endoscopes. And their latest endoscopic stack supports, it has this Clara built in. So I can imagine that in a couple of years, maybe not even years, like next year. You will have something like a surgeon will have App Store on their endoscopic stack where he could be able to buy or purchase surgical navigation software, computer-assisted surgery software, or just AI models, for example, for real-time segmentation. There are already experiments, quite well-developed work. In cholecystectomy, there is this so-called critical view of safety, where you need to see three things very clearly of these vessels of the cystic duct and artery to be able to make a safe cut. Okay, and the system already can mark this just based on segmentation, which is still not perfect, but when it detects that all three areas are clearly visible, the surgeon will just have this, huge green mark that now it's time to make a cut. So this is already this is already happening. So I can imagine a future that the endoscopic stacks will have to begin with their stores where you could download AI models which will help you to perform surgery.
I think it's a nice concept, but I think that you also need to model some pathologies, because a surgeon might face different situations and they'll be trained not on normal anatomy, but on pathology. So how to get a wider spectrum of pathologies?
Yes, so that's a very good point. So it will be very difficult to model pathologies by hands for training, because you have hundreds of cases probably to get good training. You would need probably Sano would need to hire like a huge team of computer artists, because that's 3D modelers, because that's how it's done currently in surgical simulators. Luckily, so there are two things, I guess, which are great these days. So one is are the segmentation algorithms from both CT or MRI data. So I'm actually in fact exploring this, been exploring this recently, whether we can just throw in a raw image. There are tools like Total Segmentator, and then more recently, Auto 3DSeg from NVIDIA, which can segment more than 100 different anatomies from a CT or from CT scan. And recently there was MR Segmentator, literally like a few days ago I saw this, which can segment more than 100 different classes of anatomy from MRI image. And so we can throw in the data. When we have automatic segmentation, we just need to do relatively simple processing like decimation and smoothing the 3D meshes to get basically new anatomy. And with some additional processing, because not everything is visible, like soft tissues, these connective tissues might not be there, we could generate them as a intermediary step to generate them procedurally. And then we can have whole case simulated. And this is great because it would allow us to create pretty much infinite number of cases, simulation cases, just from the images. It could bring the surgical simulation not only as a training tool, but also as a preoperative tool, potentially, which is, way bigger market. And another thing is, so that's one thing. Another thing is this generative AI models. So what we can do now with Stable Diffusion, we could potentially train it together with text and just type in that we want to have, for example, like a cancer located in this part of liver. And it will generate it, of course, when we'll manage like to train it this way. Currently, we're just feeding like surgery images and telling, okay, this is surgery for now. But it will be more specific that this is this kind of surgery, this kind of pathology. We should be able to achieve this. This is already happening when they trained on X-rays. So now by just typing in like a medical description, they are able to generate realistic images of X-ray scans.
Przemku, maybe it's too early, but a question Do you have some initial assessment? What might be the value of technology which your team has been developing? Because, for example, Marian can invest 1 million to hire several artists, but you might license your technology for 100 million. So it will be a great deal for Sano, for everyone.
Yes. Sorry, I missed the question, actually, the question.
The question was at the beginning, do you have some estimates what might be the market value of technology which has been developed by your team?
No, I'm afraid no. Like I said, we can see quite a lot of movement in research in these fields. Even NVIDIA, like the leading research teams are on it. We are working directly. We are communicating directly with Director of Simulation of NVIDIA, Dr. Miles McLean. We are in touch with Animesh Garg, their senior researchers on autonomous robots. So they are aware and interested in this work. There is some competition in terms of market value per se. The field is clearly gaining traction. I mean, the surgical robotics. I guess the question is, to what extent also surgeons would like to have it automatized, because I also don't think they would like to have it, fully automatic, that they just press a button and watch it. This is like a adrenaline rush for them, as far as I know, based on my wife's experience. So I don't think they will totally give it up, like performing the surgery in fully autonomous, like not in the manual way. But I guess there are some aspects that there are just some tedious to do, and that they would be fine, like, making it automatic. Probably it would be more in the way of like, assistive or like error prevention things.
Okay, thank you very much. And now we have Wiesław, are you going to continue your questions, or?
Oh, I think it's enough at this stage.
I'm happy to continue the discussion.
Yes, it was a very interesting discussion. I think that, well, probably it will be just to organize a separate discussion about this. Now we have Maciek Malawski. Maciek, go on, please.
Okay, hello. Thank you, Sabina, for a nice presentation. And I have a question about this Sim2Real, yeah, as Przemek said, or in the other words, about the validation of the simulation with the real robots and devices, and also some real materials. Yeah, I understand. So do you have some plans or some existing work in these topics? Because I know we have this robotic arm at Sano, and how it comes into play together.
Maciej is worried that we'll start bringing cadavers and pig livers into the lab. No, there are no such plans, at least for now. Okay, Sabina, please.
Yes.
But we are working with Matthew Możejko in adapter to translate the last step of our work as translate to Sim2Real. But generally, we will be working on some phantoms, not the real tissue. I believe so. So maybe I don't know about more.
Yes, that's correct. So this is basically standard in this group because of the bioethical issues, or also like lab conditions, especially at Sano. So we don't have this labs adapted to organic tissues. But we have our good friend Diego Dalalba, who was our visiting scientist, and in fact Diego has access to, it's called DVRK, so Da Vinci Research Kit. So this is decommissioned Da Vinci robot that Intuitive Surgical gives away to research groups. So we may apply for one at some point. So we would need more space probably for it. So he was actually, in fact, now Diego is trying to run the policies trained in our software on real Da Vinci robot. However, we would also use our robot in the lab. So as Sabina mentioned, Mateusz is creating like the adapter where we could put the at least the laparoscope. I mean, at least because normally the robot has also actuated more degrees of freedom. One laparoscope can only grasp things. And we would like to use the molds of the 3D objects to use as a target. So basically, for now, we are training sim to real, like simulation to real surgery. But later on, we would want to do something which is much simpler. So sim to real, but to silicon models, which can be, for example, like monocolor, or the environment is just simple because we just a liver like in the box. We can control the lighting. It's just much cleaner environment. But that's currently how this is being tested. A lot of work is for now is still even purely virtual without sim to real.
Yeah, I'm not scared. I mean, but
No.
we assume that we mostly focus on software here, but it's important to have these collaborations like with Diego and others who can complement this real part.
Yeah, so it's changing the dynamic about the publications because it's always higher impact when you write that you actually run the policy in real world.
Yeah.
Ideally on the DVRK, because obviously the teams who have access to DVRK will reject your paper saying, no, this is the robotic arm adapted is not something that be clinically used. You need to run it on DVRK. So that's the reality.
Mm-hmm.
And it's also like a huge spectrum, the relatively wide spectrum of potential publication directions, because we can focus on more like computing journals, medical technology journals, but also there is an increasing risk in purely robotics journals or conferences like IROS. As you know, I was presenting the simulation work in 2022. Actually, ICRA, which is the leading conference, it got upgraded to 200 points, and Core Star conference it's now. So we have one paper under review at the moment there, and we are looking next year also submitting something.
Okay, many thanks. I'm looking around for more persons willing to discuss this. Well, it seems that that was all who wanted to take part in the discussion. So many thanks to Sabina for inspiring talk, because it was a lot of discussions after your presentation. Well, and I hope that we will soon see new results. Thank you very much to all of you for participation in the seminar. And it is still not clear if we will have a seminar which was scheduled for next Monday, but definitely you will be informed as soon as it will be possible. Anyhow, we will have a seminar definitely in 2 weeks from now. So thank you very much for participation, and you are invited to the next SanoSeminars. Thank you.
Thank you.
Thank you.
Bye.